Citation of Professor Ezzinbi, Laboratory of Mathematics and Population Dynamics, Cadi Ayyad University, Faculty of Sciences, Samaria, Department of Mathematics, Marrakesh. Professor Ezzinbi is a Moroccan scholar whose research focuses on differential equations and dynamical systems. He works at the Laboratory of Mathematics and Population Dynamics of the Faculty of Sciences, Samaria, of the Cadi Ayyad University, Marrakech, Morocco. He earned his PhD in partial functional differential equations in 1997 at Cadi Ayyad University. His current areas of interest cover differential equations, dynamical systems, evolution equations, and partial functional differential equations. His research interests are evolution equations, operatory theory, partial functional differential equations, dynamical systems, and integral differential equations. He serves as an editor-in-chief and an associate editor for several mathematical journals. He has been a visiting professor at numerous universities in African, Asian, European, and North American universities. He's a member of the African Academy of Sciences since 2009. Professor Khalil has had several PhD students in many countries, including Morocco, Senegal, Chad, China, Nigeria, Cameroon, Burkina Faso, Tunisia, and Angola. Professor Khalil has supervised 20 PhD students from Africa. These are outstanding achievements for a mathematician working and living in Africa. He was a member of several doctoral dissertation committees in Africa. His works inspired many researchers and influenced many publications worldwide. Professor Ezzinbi is fluent in French and English and has co-authored several publications. He is very flexible and adapts easily to different work environments. Professor Khalil has over 270 papers indexed and 3,901 citations. His age index moved recently to 36 with Google Scholar. Join me in welcoming our own distinguished Professor Ezzinbi. Welcome, sir.
Okay, thank you very much for this nice introduction. So, can you hear me?
Yeah, we can hear you, but
yes.
if we can make it louder, I would appreciate it.
Okay, donc I would like to thank Professor Emmanuel for this kind of invitation. And then I am pleased to talk to you to one of my work that I have done recently. So the aim of this work is not technical things. I want just you to take messages from that talk. This is very important because technical things, if we need them, then we can find them immediately. So I start to share with you my talk, and I don't know if you can see my slide.
Yes, we can.
Okay. And this is about periodic solution and then attractiveness for some partial functional differential equation with lack of compactness. And then I remember I sent another title to Prof. Emmanuel. This is about wake topology, and this is included in the talk. So we use wake topology instead of strong topology to get some new results and then to apply them for several models when strong topology cannot be applied. So this talk is based especially in two papers that you see here. One is in applicable analysis in 2020, and this is the next proceeding of the American Mathematical Society. And the talk is based on the two papers. So let me just start from the beginning, and this is the talk. And you see here section 2. This is very important. This is the newty of that paper. New fixed point theorem for affine maps in locally convex space. This is more general than wake topology, because if you have wake topology, then of course the vector space provided with wake topology becomes locally convex spaces. We know this very well. And this new fixed point is just for particular maps. This is what we call affine map. And I will explain what does mean this. And then behind of this, we have a lot of application, especially in differential equation, and then dynamical systems. For example, if we need to solve the problem of periodic solution for non-homogeneous linear equation, like evolution equation or partial functional differential equation, etc., etc. I will give you some application of this new theorems. As I said, this is not, the aim is not technical things. I don't want you to take care of technical things. I want just to get messages, how to build this work, how to get our result, and what are the motivation behind of this result. So affine map. So let me just start by this Poincaré approach. Poincaré approach is the first mathematician who really studied the problem of periodic solution for nonlinear differential equation. So if you just let me remind you the idea of Poincaré map, and this is what we are going to use for affine map in Banach space. So Poincaré considered the following nonlinear differential equation, and then he assumed that f is periodic with respect to t, which means that the input function is periodic, and then he asked the following problem: do we have a periodic solution? And then you are going to see that the idea of Poincaré is very simple, but behind it we have a lot of application. And right now, a lot of researchers still using this technique. So we suppose that our problem one, this nonlinear differential equation, is well posed in Hadamard sense, means that you have global existence, at least for T to be positive, you have uniqueness, and then we have dependence, continuous dependence with respect to initial data. For example, if we assume that f is globally Lipschitz with respect to the second argument, and then of course we can prove, or you have seen it, that equation one is well posed in Hadamard sense. But in most of cases, we don't have global existence, we have local existence, and then even that, the problem can be shown to be well posed in Hadamard sense. Can you hear me?
Yes, sir. Yes, sir.
Okay, and let me just to share with you the idea of Poincaré. This is the aim of this talk. I need you to get message, because for young researchers, this is the message that I want to tell them. If they want to start research, they have to go back to the old papers and then read them very well. And there you can find the basic theory, the idea that all the researchers have developed. So let us go back to Poincaré approach. And then Poincaré said, if I want to talk or to look for periodic solution, you have just to consider what we call the Poincaré map. And then the Poincaré map is map that is defined from Rn to Rn, and P of U0, this is the initial data, this is the value of U at omega. This is the period U0, and because we assume that the problem is well posed in Hadamard sense, that means P is well defined, is continuous, everything works. And then here, listen, this is the idea that Poincaré has. If P of U0 is if P of U naught is U naught, means that U naught is a fixed point of P, then immediately you can prove that the solution starting from U0 is omega periodic. So you see that the idea is very simple. So to log for periodic solution for equation 1, it becomes to log for fixed point problem for the Poincaré map. And then now, if you need to log for periodic solution, you have just to log for fixed point of that map. And behind this, we have a lot of theorems from fixed point theory. Then we can apply them. And then we have a lot of works, lot of books, lot of papers, just where the author used the Poincaré approach. And this is some picture that I want to share with you. The first one, this is the Poincaré map. Second one, it shows you when P, when U0 is fixed point. And you see that here you have periodic solution. And then why do we need to log for periodic solution? Because it can be limit cycle limit for equation 1. Means then you can have global attractor that is given by this periodic solution. So after that, there is another idea of research to see or to prove if the periodic solution defines global attractor. So our talk, as I said, this is the Poincaré approach, and this is what I am going to use for affine map. This is the approach, and this it was discovered, I think, in 1925 or something like that by Poincaré. And this is what I am going to use. So affine map, you know this from elementary school or high school. Affine map in R, this f of x to be ax plus b. You know this very well. And then from high school or elementary school, f has a fixed point if and only if a is not 1. You know this very well. So what happened to this condition when we work in high dimension, especially when R is substituted by Banach space, and then its dimension is plus infinity. This is what we can find when we are dealing with evolution equation or partial functional differential equation or partial differential equation only, without functional differential equation. So this is, you know this very well, and this is some pictures. And if you need f to have fixed point, then you have just to assume that E is not 1. So we are going to see what does mean this. So now, what is affine map? So if you see here, affine map in R is given by this A of x plus vector does not depend on x, because the argument here is x. And what is AX? Is linear map, not linear map. This is the only linear map that you can find in R. If you take map from R to R and you say that map is linear, then it has general context is what? Is linear map applied to X plus vector does not depend on X. This is the meaning of that. Affine map in high dimension, maybe in vector space, when its dimension is plus infinity, it can be this f of x is b of x plus b. This is affine map. When b, it can be linear map or matrix. Linear map, of course, bounded. This is L of x. This is a space of bounded linear map, or it can be matrix, or it can be linear map from Rn to Rn. So before to start to log for periodic solution for some kind of evolution equation or some kind of dynamical system, the problem first is to find a fixed point for that map. So when you are in R, in scalar case, we know what this means. This, you have just to assume that E is not 1, and then you can find fixed point. You can compute it very well. So the problem here is not easy because we work in high dimension. It can be Rn or it can be X. Dimension of X is plus infinity. And then we have a lot of theorem to use taken from spectral theory or from linear functional analysis. We are going to see this in the next. So let us start by the first theorem that was obtained by two big mathematicians, Chow and Hale in 1974, and this for linear, for affine map. And let me just to show you the theorem that they obtained, because they have this problem. And this problem, u prime of t to be L u sub t plus f of t, this is what we call functional differential equation. And behind the form 2, we have a lot of models coming from population dynamic, biology, ecology, so physics, chemistry, a lot of, this is what we call daily differential equation or functional differential equation. Because the initial, this is another talk, donc I am not going just to take care of this. Just I want you to take message, and this is another theory to model phenomena in our life. Because the initial data is not vector, this is function that is taken from C. This is a space of continuous function from minus R0 to Rn. And this is the problem solved by Chow and Hale in 1974. And this is the input function. And then you want to prove periodic solution using the Poincaré map. This is the same idea that was discovered by Poincaré. So they consider the following Poincaré map from that space, because this is the phase space of equation 2. And you see this is just P of phi, u sub omega phi. And what is u of t? This is what we call the historic function. And the historic function is defined by this. U sub t is map taken from C. You apply, if you apply it to theta, this is u t plus theta. And then the philosophy behind this, because if you need to model any phenomena, you have to consider its past. And this is very natural to assume, and this is very worthy to use it when we try to model. And then behind this, we have a lot of papers, a lot of work, a lot of books. So Chow and Hale used the Poincaré map. And then this is the Poincaré map. And then they observed that this Poincaré map is affine map, because the problem here is non-homogeneous, because f does not depend on u. This is what we call non-homogeneous linear problem. And then this is u omega applied to phi, because the variable here, the argument is the function phi. And then this is u sub omega 0f does not depend on phi. You see it here. And then, of course, because u omega is what exactly is the solution without f. Is it clear? And of course, it is linear with respect to phi. And it is linear with respect to phi. And then the second vector, this vector does not depend on phi. And then, of course, this is affine map. This is an example, the first example of affine map. And then the idea of course, because this problem is well posed in Hadamard sense, we have global existence, we have uniqueness, we have everything, because L is bounded linear operator from C to Rn, and then everything works. And then we have uniqueness, we have global existence, and then we have continuous dependence with respect to initial data. So this is the problem that they want to solve. And then the problem now is to find fixed point of P. Then they forget, this is the message I want to say for young researchers. They forget the problem of periodic solution, and then they are front of another new problem. And then what is this new problem? Fixed point for affine map. Let A be a Banach space, K be an affine map. That's mean K of X to be K not X plus Z. K is bounded linear operator does K have fixed point? This is another problem. And this problem is linked to fixed point theory. And this is what they have discovered. If we assume that the range of A minus K naught is closed, here I is the identity map, and then at least you can find X naught such that K power n X naught is bounded. As the sequences is bounded, then T has a fixed point. And then if you see the proof of this theorem is very easy. It's very easy, is based on Banach, on Han-Banach fixed, on Han-Banach theorem. And then this is the first theorem that was discovered by Chow and Hale in 1974. And this is the theorem. Now, they applied this theorem to where? To that equation, to this problem, because the Poincaré map is fine. And then U of omega is compact. This is the dynamic of this equation. Because U omega, we can prove that if omega is bigger than R, and then here R is the delay, then U omega is compact. And from compact operator theory, you know that you have this condition immediately. Then I minus U omega is closed. And then if you have at least bounded solution over R plus, then this, it gives you condition double I, because you take X naught to be exactly the initial data of that bounded solution, and then you have double I, and then you can apply immediately this theorem, and then the Poincaré map has a fixed point. This is what Chow and Hale have done. So here they use strong topology. Can you see it here? Everything here, we use strong topology. And then for us, we are going to relax this theorem. We try to find some theorem like this, but without using strong topology. We use just weak topology. And this is the first aim of this talk. And then after that, we apply our new theorem to find periodic solution for non-homogeneous. This is our theorem. So you take A capital F. This is not strong topology, biotopological vector space. And we assume that A capital F is locally convex. You know what this means. F, the origin, has a basis of convex neighborhood. Donc ça, c'est classical definition. And then if you substitute F by weak topology, then you have this. No problem. So this is our theorem. And you see, is more general than using weak topology. Just we work with locally convex space. So you take capital AF to be locally convex space, and then F is continuous, you see here, and then of course K is Affine map. And then here we use continuity, but not using strong topology, using topology of F. And this is more general than weak topology. So if you assume that X naught such that the closed convex or X is F compact, means with this topology, then K has at least one fixed point in capital A. So if you see this theorem at the beginning, you can say it is an abstract result, but actually not, because behind of this theorem, we have a lot of application. And then, of course, I will show you some of them. Can you hear me?
Yes, sir. Go ahead. Yes. Go ahead.
Can you hear me? Okay, thank you. So, and then, as I said, if you substitute F by weak topology, then you get this. And then if you take weak topology, this condition is equivalent to what? Just to say that this is bounded. Do you understand? If you substitute capital F by the weak topology, then this condition becomes what? K power n X naught is bounded. Because if you work in a reflexive Banach space, for example, If it is bonded, then it is weak compact. So this is another theorem also for Affine map and locally convex space. If compact, then you have at least one fixed point in capital A. This is the closer it's compact. Yeah, this is the theorem. So if you are in Banach space, then it becomes Banach space such that, yeah. So this is another theorem, just corollary of the first one. If you are in Banach space, this is Affine map, and you assume that this is relatively weakly compact, then K has at least one fixed point. Mean we use here weak topology. So this is some classical, some corollary that we obtained of this. If you work, of course, in reflexive Banach space, then you know that if K power n x naught is bounded, then of course it is weakly compact. Then of course K has a fixed point. So if you compare our theorem with Chow and Hale that was obtained in 1974, our result of course is better. And then it has, of course, a lot of application. Then we are going to say them. When we cannot use strong topology, then at least we can use weak topology. This is exactly yes. Our theorem obtained by Hale and Chow becomes, of course, particular case of our theorem. So this is some message that I want to share with you. To find theorems is very nice, but the problem is to motivate them. And then the best way to motivate them is to find application. Application, when classical theorem cannot be used, then you can justify your theorem, and then it will be very good for what you have obtained. So let us start by evolution equation. This is some kind of non-homogeneous linear equation. A, this is the generator of C0 sum A group. And then we assume that the input function is omega periodic. And then you can see that the Poincaré map is affine. Just we use this variation of constant formula. And then this is some example. Evolution equation. And then behind this, we have partial differential equation as an example. So the Poincaré map is affine. Then if you try to apply our result, then you can find a fixed point of P. And then that fixed point is the initial data for a periodic solution. So let us go back to the first example that I give you about Affine map in R in scalar case. That condition E is not one. What does it mean in high dimension? And then we need to do a lot of spectral theory. And then let me just to start by this definition. This is what we call the essential spectrum for B. And then the essential spectrum of B is defined by this. This is lambda in the spectrum, such that at least one of the following conditions is satisfied, the range or 2 or 3. And this part is very important in the spectrum. And then if you are dealing with this part, you need to control it very well, because otherwise you cannot do anything after that. And then we define what we call essential spectrum is defined by this. And then this is the essential norm. And then essential norm is exactly, this is the same norm of using strong topology, but here we use measure of no compactness. So, and this is the condition that we have seen in R. What does mean this in high dimension? Means that you have to compute, you have to do spectral theory, you have to compute the essential radius of P by this formula, and then you have to find this condition. This is the meaning of this condition in scalar case. So if you have this condition, it means that one is not in the essential spectrum of that operator. And now, if you go back to definition of the essential spectrum, means the range is closed. If the range is closed, then you can apply the previous theorem that we have seen by Hill and Chow, because you have this condition. Don't forget, this condition is very important on that theorem. And then this is what you need. And behind this condition, believe me, a lot of work. Spectral theory, and then essential spectrum, and then essential reduce. And then you have to check that you have this condition. And then you can apply Hill and Chow theorem. And then, of course, you can have at least one omega periodic solution. So let us see this corollary. It says what? If we suppose that this is compact, of course, you know why do we need this condition? Because we look for I minus T omega to be closed. That's why, because if this is compact, then the range of I minus T of omega is compact. And then, of course, you can apply those fixed point theorem for affine map. But my problem is here. When you model, we don't have this condition. So if you have this condition, means that you are lucky. But most of models that we study, we don't have this condition, because we work in dynamical systems that are well posed in high dimension. And then the phase space is dimension can be plus infinity. And then our theorem will solve this case. When T omega is not necessarily compact, then what happened? And then this is an open problem that was also posed by Hill, I think in 1975 or 7. He wanted to extend his theorem for functional differential equation, not in Rn, but in Banach space. And then at this time, he couldn't solve the problem. So what we are going to solve, some of those problems. So look at, if we apply our theorem, if there exists X naught such that this is bounded, this is nothing, we can have it. This is relatively compact, means that the closure is compact, then equation has an omega periodic solution. No, this is no problem. And the most, yes, if you suppose that there exists X naught such that this gamma plus X naught is relatively weakly compact. For example, if it is bounded and you work in reflexive space, then you have this for free. Then you can have equation has an omega periodic mild solution without assuming that T of omega is compact. Yes, you see here, if you are in reflexive Banach space, then this is bounded, then immediately you have an omega periodic solution. Yes, this is some corollary of this. So we go we go here for another extension, and then there is no need to assume that the semi-group generated by A is compact, but only the resultant operator is weakly compact. But if you work in reflexive Banach space, then you have this condition, no problem. Weakly compact means it takes bounded state to say that he is relatively weakly compact. And then this is equivalence. You have equivalence between existence of bounded uniformly continuous solution over R plus, and then existence of an omega periodic solution. Uniqueness here, you can prove that the periodic solution can be global attractor. If you assume that the C0 semi-group is stable, then we can prove, and then this it has been proved in that paper published in Proceedings of the American Mathematical Society. This is some example, and then I can close my talk. This is some example taken from population dynamic, And you can see the example here. This is a model that is given by partial differential equation. I'm not going to give you the details about the model, but it has a lot of application in population dynamics. This is partial differential equation. And then we assume some technical assumption. We select the operator domain of A is exactly that linear par you see here, and this is the input function. And then with this transformation, you can see that the model 3 is equivalent to 4. We work where here? Our phase space is in that space, that is a Hilbert space. Of course, it is reflexive. Then, if you have bounded solution over R plus, then we apply our theorems, then you can find an omega periodic solution. This is another application for functional differential equation. This is in Banach space, not in Rn. Chow and Hale studied equation A in Rn. And then in Rn, you can apply Ascoli-Arzela theorem to find compactness. Here, we don't have compactness. And then we apply our theorem. So if we assume that equation 1 has at least bounded solution over R plus, then you have an omega periodic solution. This is another example also for functional differential equation. And then here we construct the bounded solution over R plus. This is some example of partial functional differential equation. So on, we have a lot of application. I think I am going to stop here. If you need this work, I can send it to you, no problem. Transport equation also with delay. We have a lot of application with delay. The idea is the same. And then I want to share with you some references related to this work. And then thank you very much for your attention. And then if you have any question or comments, I am here to respond to you.